Welcome, this is lecture 50. In this, we want to prove a relation between the Laurent polynomial Qm, which is the denominator in the way we wrote the Hilbert series, and the Hilbert polynomial Pm. So it's not very surprising because the difference between the Hilbert polynomial and the Hilbert function is only in some finitely many degrees. After that, the behavior of the Hilbert function is the same as the behavior of the Hilbert polynomial. Okay, so if you write the generating function for both of these, then asymptotically we should get the same behavior, and the denominator should be the same. So it's not very surprising. But so let's explore this let's try to understand this. Okay, so we continue the notation. R is a polynomial ring over a field in n variables, and M is a finitely generated graded module. Okay, and we have various things that we have defined so far. Okay, which is we know the Hilbert series. Then this is of the form Qm 1 minus d to the d. So let's put d to be the dimension of M. Okay, and then we also have Pm, okay, which is the Hilbert polynomial. Okay, so here's a proposition. We know that the Hilbert polynomial itself was written as some constants, integers, which depend on M, okay, and it went from 0 through n minus 1, okay, times pi of pi. This was the binomial looking polynomial. Pi of x was x choose I. Okay, so it's like a binomial function. Okay, so assume so write P as this. Then, so what is this expression's relation to the Hilbert series expression in terms of the Hilbert series? Then ei of M is 0 for all I greater than or equal to d, the dimension, and ei minus 1 of M equals the Qm1. Okay, this was a number that we had studied and established was that this is a positive integer in the last proposition. So this is the number of copies in which the top degree binomial polynomial pi shows up. So this is non-zero, and this is these are the ones above that are 0. Sorry, this is d minus 1. Okay, so definition. This number here is often called the multiplicity of d minus 1m is called the multiplicity of. We'll see this when we look at projective geometry. Multiplicity of M. Okay, so proof is not it's just a sort of not very difficult at all. I mean, we're just comparing. Okay, so notice that there exists some J0 integer such that the Hilbert function, okay, rank of Mj equals Pmj for all j greater than or equal to J0. That is that this is true. There is a polynomial with this property is how we defined Pm. What gave Pm. Okay, so this is true. So therefore, if we look at the following two sums, Hm of t, this is the generating function for this sequence of integers, and on the other hand, we look at this. So notice j inside n. That's because Pm need not be. Sorry, let's clarify this. P Pmj t to the j is a Laurent polynomial. Okay. We want to restrict this to the positive non-negative part, because if we work out what the value of Pm if you work out what the value of Pmj is, well, that will depend on what the value of this binomial polynomial Pi is, and it is 0 for some short interval 0, -1 and so on. After that it becomes non-zero, and from one it's 0 for a short interval which includes up to -1. So -1, -2 and a few numbers, this function will take value 0, and thereafter for larger and larger, smaller and smaller integers, more negative integers, this polynomial takes a non-zero value, and one would expect the same behavior for Pmj also. So for j sufficiently small, this will be a non-zero thing. So this, okay. So we want to sort of restrict the right-hand side to the non-negative integers, and left-hand side we don't care. The point is that the difference, so there will be some t to the minus exponents coming from, might be there from this part, but eventually for j greater than or equal to j0, this will cancel each other. Okay, so this is a Laurent polynomial. Okay, so so now Hilbert polynomial itself is a Laurent polynomial divided by 1 minus t to the d. This we established. Okay, so now if you take h and subtract a Laurent polynomial, we will get that this is also of the same form. So therefore, there exists a Laurent polynomial R of t such that Pm sum of Pmj t to the j, okay, j inside n is j inside n is R of t divided by 1 minus t to the d. Okay. So we get this thing. On the other hand, if we take each one of these binomial polynomials, okay, if you take Pi, then take its value at j and then Tj, and then do the sum. Okay, this is easy to check that this is of the form 1 minus t to the 1 plus I. Okay, in fact, we earlier observed that Pi is the Hilbert series of a polynomial ring in I plus 1 variables, and this is exactly the Hilbert series of that polynomial ring. So this is, one can check this directly. So this is a Hilbert series of a polynomial ring in I plus 1 variables. Okay, so this is the basic thing. So therefore, if we take Pmj Tj, j inside n, okay, this can be written as, so each of those is multiplied by e to ei divided by 1 minus t to the I plus 1. I goes from 0 to n minus 1. Okay, and we can rewrite this as, okay, so make the so here the denominators are different, make it the same. Okay, so we would get 1 minus t to the n minus 1 minus I, okay, EIM. I goes from 0 to n minus 1, so that's the new numerator, divided by 1 minus t to the n. Okay. Now we know that the left hand side has, so this is going to look like R of t divided by 1 minus t to the d. Okay. We can multiply on both sides, okay, by 1 minus t to the n. So we would get therefore that 1 minus, therefore we will okay. So if you multiply both sides, okay, we would get 1 minus t to the n times rt equals this quantity. Okay. So therefore we will get that 1 minus t to the n times rt, n minus d, rt is that sum on the right side. So to n minus 1. Okay. What does that mean? Okay. So it means, so just formally we can just think of this as maybe s to the n minus d times, not rt, r of t. So r of 1 minus s. Okay. So this is some polynomial, it doesn't matter, equals sum of EIM, and EI is the coefficient of s to the n minus 1 minus I. So on the right side, the first, the coefficients of s, coefficient of no constant term, coefficient of s, coefficient of s square, all the way up to coefficient of s to the n minus d minus 1 vanish. Okay. So therefore, now let's rewrite that thing. Therefore, for all I greater than or equal to d, okay, EI of m, okay, is 0. Why? Because since it is the coefficient of 1 minus t. So this I am just writing to explain. I'll just go back to the, okay, so just an aside. All that we want to say is that if you write this, if you think of 1 minus t as the variable, then it cannot have coefficients in small degree. Okay, coefficient of 1 minus t, 1 minus t to the n minus 1 minus I, okay, and n minus 1 minus I is less than n minus d. Okay, that is, coefficients for every exponent less than n minus d is 0. That's all that we have used, and this gives this conclusion. Okay, so that proves that statement. Okay. Okay. So hence we can write QMT 1 minus t to the d as HMT, which is, now we only worry about up to d minus 1. 1 minus t to the, since we have now divided by n minus d on both sides, this just becomes d minus 1 minus I, EI of m, divided by the sum, the entire sum divided by 1 minus t to the d. Okay, plus some Laurent polynomial. Remember, this expression was for, this is for PM. PM differs from HM. I mean, this is for the generating function for PM for the non-negative degrees. That differs from the Hilbert series by some Laurent polynomial. Okay, where R1 of t is a Laurent polynomial. Okay, so now what we need to make the denominator same, then compare. Okay, so therefore Qm of t is this quantity plus 1 minus t to the d times this. I goes from 0 through d minus 1, EI of m times 1 minus t d minus 1 minus I plus 1 minus t to the d times R1 of t. That's how the numerators would look like. And this now implies that Qm of 1, all of these terms involve a 1 minus t except the topmost, and this involves a 1 minus t. So Okay. So this is the proof of d minus 1, the last non-zero. Okay. So this is a description of the multiplicity. This quantity is called the multiplicity. This ed minus 1. So it is the coefficient. It is the coefficient of the largest j, such that pj, the binomial looking polynomial pj, appears with a non-zero coefficient. So, okay, so this is what the multiplicity is. And now we want to do to understand this for ideals for future meaning in the next one or two lectures, applications towards projective geometry. Okay. So proposition. How would one do? So one can of course do this for modules also, but I don't plan to do it to apply it in that generality, and perhaps the better intuition is there when one works just with ideals. Okay. So now let I be a homogeneous ideal. Okay. Write its primary decomposition, irredundant. So let I as intersection of some ji, I goes from some 1 through m, okay, be an irredundant, meaning the radicals of the ji's are distinct primes, pairwise distinct primes. There is no there are not two different ji's with the same associated prime. Irredundant primary decomposition. Okay. Assume that, meaning we have ordered the ji, assume that dimension of R mod I equals dimension of R mod ji for the first S of them, and dimension of R mod ji is less than dimension of R mod I for the remaining. Sorry, S plus 1 less than or equal to m. Okay. So we have arranged the ji so that the first S of them are the ones which have maximum dimension, and the rest of them have smaller dimension. Okay. Then the multiplicity of R mod I is the sum of the multiplicities of R mod ji's. D here is the dimension of R mod I. Okay. The multiplicity of R mod I is the sum of the multiplicities of the R mod ji's, where those are the associated components, those are the primary components for the associated primes of maximum dimension. Okay. The other ones don't count in this calculation at all. Okay. And we will see a geometric reason behind this once we go away. So far we have seen rings and ideals and correspondingly some k to the n and algebraic varieties inside k to the n. That's not, I mean, we'll change that picture a little bit. Now we'll worry about what is called homogeneous prime spectrum, and that will be there we can see this. I mean, we'll see what this means. Okay. And then we will see how these can be computed quickly, etc. Okay. Or at least some ways of computing them quickly. There are other ways. Okay. So this is what we want to prove. So proof. Okay. So we will first. Okay. So let K be this intersection of Ji. I goes from 1 to 1 to S m minus 1. Let's split them by the dimension. Let J be the intersection of the Ji. I goes from 1 through S. So this is a primary decomposition of J, and all of them have the same dimension. All the components have the same dimension, and J prime be the Ji I goes from S plus 1 to M. Okay. So then dimension of R mod J is D, and dimension of R mod J prime is less than D, because all the components there have smaller dimension. Okay. And J intersect J prime is I. Okay. So now from this exact sequence, okay, so from this exact sequence, okay, what do we know? So we know that this has smaller dimension. So this one's Hilbert series will grow at a, I mean, the denominator would be 1 minus t to some exponent which is less than d. For this, the Hilbert series will actually add because it's a direct sum. This one's denominator will be 1 over 1 minus t to the d. This will be smaller because this dimension is smaller. Okay. I mean, dimension of this is less than d. This is a quotient, so this dimension of this is also less than d. The map is, if we take some a bar comma b bar here, that goes to a plus b bar, or maybe write it as a minus b bar. Okay. Bar denotes the appropriate values. Okay. And here the map is some a bar goes to a bar comma a bar. That's the map. Okay. In this, so this term here and this term here have smaller dimension. Okay. So if you write the Hilbert series of the middle term, H of the middle term. So for simplicity, let's call this thing M prime. Let's call this M. Let's call this thing M prime. Let's call this whole thing M, and this is M double prime. Okay. Then H of M, the middle one, T is H of M prime plus H of M double prime. Okay. So this is of the form some Qm over 1 minus T to the D. M prime is T to the D, that's the leftmost one, plus Qm double prime over 1 minus T to the E, where E is less than D. Okay. So when we rewrite this thing, we would get Qm prime plus 1 minus T, okay, to the D minus E, which is a positive, Qm double prime over 1 minus T to the D. And when we evaluate the numerator at 1, only this will show up. So now this shows that Q of this shows that this thing here, for the middle one, so the multiplicity of R mod I is same as the multiplicity of this sum. This implies that E d minus 1 of R mod I is equal to E d minus 1 of R mod J direct sum R mod J prime. Okay. Now repeat the same argument for the direct sum. So the direct sum gives another short exact sequence. Okay. 0 to R mod J to R mod J direct sum R mod J prime to R mod J prime to 0. This is just projection maps. This is a projection map, that's an injection map to that factor. Again, for same dimension consideration, this part has smaller dimension. Okay, so by same considerations. Okay. E d minus 1 of R mod J equals E d minus 1 of r mod j direct sum r mod j prime. Okay, but this is what we had said is we are already concluded is equal to r mod I. Okay, so in other words, we have removed all components from I of strictly smaller dimension. I mean, yeah, one could have argued it by removing one component also. This is just an. But anyway, we have now replaced I. We can now replace I by j if we want, and assume that all components of I have the same dimension. Okay. Now induct on S. S is 1 implies that j equals j1. Okay. So then there is nothing to prove. So this is okay. S greater than 1 means write k to be j1 intersect all the way up to js minus 1. Then j is k intersect js. All of them have the same dimension. Now use the same short exact sequence and conclude. Use the short exact sequence 0 to r mod j to r mod k direct sum r mod js to r mod k plus js. Okay. Notice that both of these have the same dimension as r mod j, but k plus js has to have smaller dimension. Okay. Dimension of r mod k plus js is less than d, since there can't exist a prime p in spec r such that dimension of r mod p is d and d contains k, and p contains k and p contains js. Because the minimal primes over these things, all of them have the same dimension, are incomparable. So if one has to contain at least 2 of them, then they must have positive, it must have smaller dimension. Okay, so this is what we need. Okay, so therefore now induct. So what we have now concluded is that therefore E d minus 1 of r mod j is E d minus 1 of r mod k plus E d minus 1 of r mod js. So we have split one component and added this, and now induct and then we're done. Okay, so this has applications towards what is called degree of a projective variety, what we will define it, and we will discuss that in the relation of all of this and to projective geometry in the next few lectures, 1 or 2 lectures.